You know, guys, if you cannot see it, or if I should write bigger or not. I think we are. Yeah, thanks. I'll do it. I'll do it. Let me do it. Let me do it. But then leave it to me. Can I keep it? Okay. Thank you. The example that we sort of treated yesterday. So recall the example. Is it visible? No. Nice. Because I think maybe it's still, let me try this other guy. About now? Okay, so we have this example. I don't know, do we have some paper? Because I think it's just because it's still wet from the cleaning. Do you have some napkin or stuff? Oh, yeah, okay, yeah, let me try this. Yeah, thank you. So basically, the example we had yesterday was this one. Was a very simple example. Was x dot equal x and y dot equal minus y plus x squared. And we call this in general, basically we call this x dot vector equal to f of x and not t. Right? So this is basically our dynamical system or ordinary differential equation. And so really to understand the dynamics of this system, which is very trivial, you know, if you really want to do it, you have to do a little bit of work. But the result was this one, that basically there is a fixed point here at 0, 0. We call it basically P yesterday, and then we looked at the stable and the unstable manifolds of this fixed point, which was basically the stable manifold was here of P, we call this P, and the unstable manifold, you have to do a little bit of work, which is just using the center manifold theorem, if you're interested in how to derive it. And then we said, okay, you know, now I know exactly how the phase space of this nonlinear system is going to behave, right? Okay. So, you know, this is how trajectory would sort of, you know, behave. Okay. So now the question is, but this is basically, all this construction actually, in general, when you do this construction, these are only local, and they really allow you to understand the behavior of the system in the vicinity of the fixed point, unless you can show that these manifolds are global, blah, 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 but this is very, you know, non-common, right? So now the question that I want to raise is that, you know, how do we study the behavior of the system of a system? Well, I mean, this is basically as general as it gets. I can make it time dependent actually, right? The behavior of a general system, let's say x dot equal to f of x and t. I can also make it now time dependent, where x, let's say, is in Rn. Say, this is 2 dimension, could be 3 n dimensions of a system. When we are not close to a fixed point. I mean, usually you can also use this technique also when we are close to a fixed point, but I want to say, okay, what happens if now this is going to tell you, for instance, how things will evolve. Let's say if I start a patch of material here, I'm going to say, okay, if I start here at the initial time, this guy is just going to squeeze here, right? This blob you can think of it as a set of initial conditions, right? But the question is, so this is basically, at t0 at a certain time t is going to arrive there. And the other question is, but what happens when I start something here? Right? Because remember, all this construction, if you really go to the books in center manifold theorem, etc., these stable and unstable manifolds usually are local. That means basically they allow you to understand how the system, non-linearly in this case, behave near a fixed point. But what happens anywhere else? What happens when you don't have a fixed point, right? So when there is flocking, etc. Okay, so that's what we are trying to do now. And so this is the question. And the first basically observation or note that I want to make is what Anupam just highlighted, which is basically the difference between Lagrangian coordinate and Eulerian coordinate. Okay, so when you have a dynamical system, you have basically this guy x dot is equal to f of x and t. Okay, this could be a velocity field. In all our applications, it's going to be a velocity field, but can be also firing the dynamics of neurons or gene expressions or anything you want. And you're going to have basically a certain initial condition. So you have to give an initial condition. So x at certain time t0 is going to call x0. It's going to be called x0 that you specify. And then what you're going to do, you're going to have you're going to define a so-called flow map, which is basically the Lagrangian trajectory of this system, right? So you're going to have basically that the flow map, f, we're going to call it from t0 to t of x0, is going to be something that is the initial condition plus the integral from t0 to t of the velocity field f evaluated along trajectories, which is f t0 tau x0 comma tau d tau. This is the flow map. This basically maps an initial condition x0 at time t0 to its later position, later or time t position. Okay, this is clear, right? Right, so I just integrate. This is what MATLAB does when you want to compute trajectories from an initial time t0 to a final time given this initial condition. So when t is equal to t0, you recover the initial time, and then this map is just a trajectory map. Okay. Now it's key to appreciate this difference, that basically the derivative of trajectories d dt of f t0 t of x0. This is the trajectory, right? So the time derivative of this flow map is equal to what? Do you know what is this equal to, guys? Can you tell me what I should write here? What is it? Is it this? It's just a very delicate thing, but it's very important to appreciate it. What is this? This is the velocity field. This is the derivative of the trajectory. Is it equal to the velocity field? It is equal to guys, if you differentiate this with respect to time, what is it? You can read it from here. What is the derivative of f with respect to time? In which one? Can you tell me exactly what to write? Yeah, so the velocity field and?
Evaluated at time.
Yeah, evaluated at time t, yes, but where?
Defined by f tau t naught.
Very good, yeah, this is very important. So this is very different from that. So when you differentiate the trajectory, when you differentiate the flow map, you always have to write that the velocity needs to be evaluated along the trajectory and at that particular time. This is a key distinction. This is key, okay? Because, if you start doing averaging of f, this guy, if you don't tell him, hey, you need to evaluate me along the trajectory of this particular guy, x0, it's never going to know that this guy is going to sample different points in space. So this is a key difference, right? So this is basically velocity along trajectories. And we are going to see when this is going to pop up later in, maybe in 20 minutes or so. Is this clear? So what is really the beauty of this? If you really think about it, in this is a velocity field, right? So remember, let's do maybe a mini schematic here. So I have let's say my grid. I'm going to do it in 2D. So this is now, let's say, your domain. Okay, so this is now my Eulerian grid. This is just, some xi, okay, vector. Okay, so the velocity field F is, and here we're going to have always, a vector field at any point, okay? If you start doing statistics of F, you can always pick x and t independently. At any time, I can say, at time 1, I want to pick a particular x. At time 2, I want to pick another x. But instead, when you go into Lagrangian coordinates, this is now the Lagrangian coordinate. Why? Because basically, the way to appreciate it is that, let's say now this is at time 0. At time t1, I can do the same. And I can say, okay, now I'm gonna just pick a time t2. I'm gonna pick either another velocity here. I can just compute f at xi t2. This was now f at xi t1 or t0. Okay, and I can always do any statistics I want. However, now when you go to the Lagrangian coordinate, what you're going to do, the only thing you can pick is your initial condition. So in the Lagrangian coordinate, you're going to sort of parameterize your space. This is Lagrangian coordinate. You say, okay, you know what, this is now my x, let me put it somewhere else. Let's say I actually can put it here. So this is my x0, this is my particular initial condition that was living there, okay, at the initial time. And I'm going to feel, of course, at the initial time, I'm going to feel, let's say, I'm going to feel the same velocity, right? This is now f of x0 t0. It's going to be exactly the same velocity. Why? Because f, if you evaluate f at t equal to t0, this is exactly x0. So it's the same point because we just picked the same point. But as long as you start going forward in time, there is no way, once you pick that particular guy there, this guy now is basically percurred the trajectory. Let's say he started here and did that. So at time t2, the only way you can do is sample this point. If you parameterize space. Once you pick x0 at the initial time, there is no way that you can have another degree of freedom of choosing space. That guy goes with his own car, and it just you follow. It's like you go with the car and you sample the temperature, but you're not the driver. You can just pick the initial position, and then you go by that and you sample different places in Hyderabad, and then you say, okay, now I do this average. I just pick the initial car. You can think of x0i as a color, or someone that every x0i is a different hat or different colored car, and then these cars will go sample, and this is basically the Lagrangian coordinate. So the one is a velocity field along the trajectory. So here you're going to sample a velocity field. At this time you're going to sample this velocity field. Okay, this is now f at f t2 t0 of x0i t2. Okay, and here instead, if you are still in the Lagrangian coordinate, likely you're still sampling this guy, which is not necessarily the same of the one before. So this is a very important distinction. Okay, so basically, in a nutshell, Lagrangian coordinates allow you to pick spatial position at one particular time. If you pick it at this time, all the rest will follow. Okay, you can also pick it at a later time and you integrate backward in time, but there's going to be always a one-to-one correspondence between a particular time t position and an initial position. Okay, that's a very important distinction. Okay. Okay, let's compute the flow map for this system. Okay, so I'm going to try to squeeze it here. So let's compute now the flow map. Flow map for this system. And you do basically this integration, or you ask Mathematica to do it. And then you should do it now. ChatGPT is, I think, is getting better also at this. But you're going to get basically the x component, which you can also call it x scalar. It's a function of t0, x0, t. Okay. What I did, so the other important thing is that usually if you have a time-dependent system like this map depends always on two times, the initial time and for how long you go. Okay. If you instead are time independent, there is only one time that matters, which is how long you go. The initial time never matters. So that's why I'm going to call it just t. I don't need two parameters for time. So this is going to be x0 e to the t. This is the x0, the x component of the initial condition. And this is going to be now y of x0 vector t. This is going to be y0 minus x0 squared over 3. Okay, e to the minus t plus x0 squared divided by 3 e to the 2t. Okay, that's basically the flow map of this system. I think I'm going to keep this side. Okay, so that's the flow map that we can just compute. Okay, so now remember, what did we actually do before? With the classical, asymptotic structures, or what you really learned in, elementary, classical nonlinear dynamics, what you do, you go to the fixed point, you linearize the dynamics near the fixed point, and then you construct these structures. Okay, so what we're going to do now, instead of sticking to this particular initial condition, x0 equal to the fixed point, we are just going to linearize along trajectories everywhere in this space. Okay, so we're going to look at linearized dynamics along trajectories. Yeah.
So how to calculate this flow map for the system?
You have to integrate the differential equation. So here is just doing that. You integrate the velocity field.
Till some time.
Yeah, till some time. Time is going to be a parameter. In fact, it's here. Yeah. So you plug in a value of time and where you started, and this is going to tell you exactly where you arrived. Yeah. I mean, in most cases, you cannot really calculate it analytically. So you have to do it numerically, like Anupam was saying. Okay, so let's linearize the dynamics along trajectory. So what does it really mean? This means basically that now I start at this point, x0, and I have a particular trajectory. This guy is called now f of, let's say I'm going to keep it general also for the general time-dependent case. So this is going to be f of t0t of x0. Okay? This is one of them. Let's say it's similar to this one. And then what you say is, okay, let me actually look at a friend that starts nearby. Let's say you start here. Let's say this guy that is a closed initial condition, and I'm going to call this perturbation vector epsilon times zeta 0, where epsilon is small. Okay, so this is just telling me that basically epsilon is a small parameter that tells you, okay, I start close by. And if I now advect this, I compute the trajectory of this guy is going to arrive somewhere here. Okay, so this is now going to be my new initial position is going to be x0 plus epsilon zeta 0. This is my new initial condition. This was x0. Okay, and this guy is going to be what? ft0t of x0 plus epsilon zeta 0. Okay, so zeta 0 is going to allow me to pick a different orientation, and epsilon is going to set the how far I start from. Okay, and okay, this is basically epsilon is small, greater than 1. Okay, so this is small perturbation, and small perturbation, or the amplitude of the perturbation. Zeta 0 is just a perturbation vector that is in the same space that you are in. If you're in 2D, you can span all the possible points in the circle that has radius epsilon. In 3D is a sphere, blah blah blah. Okay, and now, how do we compute? You want to understand a lot of information, like we did there. We asked, if I start nearby, will I go back to the fixed point, or will I go away? So eventually, what's the interesting dynamics is understanding if this initial perturbation, what's going to happen to this initial perturbation. So the question is, how do we compute now this vector? Okay, I'd say it's very simple. So we say, okay, this guy is this guy minus this guy. Right, so we're gonna say, okay, f t0 t of x0 plus epsilon zeta 0 minus f of t0 t of x0 is equal to what? Well, I mean, so usually you want to oh yeah, so usually you want to do Taylor expansion, because this is the small parameter. Okay, the only reason you can do Taylor expansion is because this guy is regular in X. Usually you always forget to check these things, but let's say if f is not even continuous or differentiable in X, you wouldn't be allowed mathematically to do a Taylor expansion. You can do it with a computer, but then the results are sort of a little bit arbitrary, right? So make sure, so in all the Navier-Stokes equation, etc., because the velocity field has already two spatial derivatives with the Laplacian, so we know from results in dynamical systems that also f has at least two spatial derivatives, so I can legitimately compute this Taylor expansion. So I do that, and so this is going to be what? It's going to be f of t0 t at the base point, x0, plus the derivative of f, the gradient of f with respect to f depends only on x0. Remember, the flow map doesn't depend on the Eulerian grid anymore. It's just a function of your initial condition, the grid of the initial condition. So this is going to be a gradient, which is going to be a gradient with respect to x0. I'm not going to write it anymore later on. Of t0 t evaluated at x0, so evaluate the Taylor expansion at the base point, which is x0, times the perturbation, which is basically epsilon zeta 0. Okay, plus order epsilon squared. Let's say that this guy has unit norm, because I already encapsulated the norm in epsilon, so I don't need to have this redundancy. Okay, well, now this guy, the difference of this quantity, so the difference of this quantity is going to be basically epsilon zeta t. Okay, this is exactly the leading order variation of this distance, and this is nothing else that, this is that minus f0, right? This was exactly, f at x0 plus epsilon zeta 0. I have to resubtract f of x0. Okay, so when I do this subtraction, I'm going to get exactly that epsilon zeta t is equal to grad f x0 t0 t of x0 times epsilon zeta 0. Okay, and therefore basically in the limit of epsilon going to 0, which is what we are doing, it's basically a Taylor expansion, we are going to get 1, which is basically that the dynamics of this perturbation vector is going to be that. So it is going to be that zeta t is equal to grad f t0 t of x0 times zeta 0. So we're going to call basically this perturbation, we can think of it as a material fiber. Think about a little basically piece of material, which is this initial segment that is going to be stretched, transported, deformed by the flow, and this is how it evolves. So at a later time, is going to be governed by basically the Jacobian of the flow map, or the trajectories, the derivative of trajectories with respect to initial condition times your initial perturbation. So this is perturbation evolution over a finite time, t0t. Okay. Okay, what is now the geometric, the geometric meaning of this? So geometric meaning is also very simple. Basically, at any initial conditions, so let's say this is our phase space, let's say x1, x2, x3 to xn. Let's pick an initial position, x0, okay? That's our base point. And then we are saying, okay, let me consider now a neighborhood of this initial position. It's basically a sphere in this space, okay? And everyone, so let's say this point is gonna go to its final position. So this is gonna be ft0 t of x0, okay? That's basically the center. And then, what happens is that every initial point, basically, that is parameterized by zeta 0 on this sphere of radius epsilon is gonna go somewhere here, right? So this is gonna be now the epsilon t. If you do for all the points, what you're gonna basically get an ellipsoid. I mean, this ellipsoid is also gonna bend, but because we truncated the approximation at leading order, there is no information about bending, okay? So they're all here. Okay, so that's it. So basically, now for every zeta 0 at xt, I'm gonna have this mapping. So I'm gonna basically populate this ellipsoid. Okay. Okay. So let me see now what I have to skip because we have less time. So basically, what is this equation governing? Is governing the evolution of every possible material fiber in this vicinity of x0. It's going to tell me exactly how each point on this sphere is going to deform under this flow, under the trajectories. Okay.
Question.
Yeah.
So at the initial when you put the perturbation epsilon times zeta 0,
Yeah.
zeta was the angle of the perturbation and epsilon was the amplitude of the perturbation.
It's not the angle. Zeta 0 is a unit vector.
It's a direction and magnitude.
No, zeta 0 is magnitude 1. I mean, this is, you can, if you want, you can always basically, you can put magnitude and the direction in zeta 0 and forget the epsilon, as long as you remember that zeta 0 is small, because you want to do a Taylor expansion and you need a small parameter.
So what does zeta 0 represent? Is it, so magnitude is epsilon.
Yeah, so basically this is it. So basically epsilon is the radius, so this is 2 epsilon, the radius of your neighborhood, the initial, and zeta 0, it's a vector that tells you how you orient. So if you're in 2D, that would just be one angle. If you're in 2D, it's going to be 2 angles. In 3D, it's going to be 3 angles, blah, blah.
Okay,
So
at the final time, so you are saying that zeta 0 is changing to zeta t.
Yeah.
That means the amplitude is also changing.
Yeah, the amplitude is changing. That's why, in fact, the amplitude of zeta t is different than the amplitude of zeta 0. Yeah. So they will still be order epsilon, the epsilon times zeta t, but zeta t itself is not unit modulus anymore.
Yeah, exactly. So that's what.
Yeah. Zeta t is not going to be unit modulus anymore. Yeah. I mean, it's easier to bring the epsilon is easier because then when you take the limit from here to here, you can recover this equation. You can take the limit of epsilon going to 0. But otherwise, yeah, I mean, you can encapsulate both in the zeta. Okay. Okay, so let's actually also do, let me see if I can, this I'm gonna skip. Okay, so now let's compute So this is, so in a little bit we're gonna basically now introduce the Cauchy green and the finite time Lyapunov exponent. But before we go there, let's try to compute now the Jacobian of the flow map for our example. Okay, so let's say for instance, so we know that now the Jacobian of the flow map is the guy, so the flow map tells you how a base point moves. The Jacobian of the flow map tells you how a little perturbation evolves. Okay, now let's compute the Jacobian of the flow map for our example, right? So for this example, let's put it here. So for this example, it's basically very simple, right? So you're gonna compute gradient of x0 of f t0 t of x0. What is this? Basically, it's gonna be a derivative of the first entry with respect to x0 e to the t. Okay? Derivative of first entry with respect to y0 is 0. Okay? Derivative of the first entry with respect to the x0, you have to differentiate with respect to x0. You do the calculation, it's going to be 2x0 e to the t. And the derivative with respect to y0 is right here, is e to the minus t. Okay? Okay. So this is going to tell you precisely all the information. So you start at any, the only dependence on the initial condition for this simple flow is on the x0. So it really depends on where you are in this axis. It doesn't really care about where you are in the y-axis, for at least for this leading order perturbation. And this is basically the Jacobian of the flow map. Okay. So now with this information you can ask interesting quantities. Okay, so I'm gonna keep that there for that system, but you can start asking using one, some exercises that you can do is, one is what are the initial position of points x0 and material fibers zeta 0, so basically what points and what directions that will be stretched the most over a time interval 0t. Okay, you can ask that. Let's say you have to. Let's say someone is going to tell you where should I deploy some dumbbells. The one that was Anupam was telling us yesterday in the viscoelastic fluids, and in which direction I should place them, such that over this finite time I'm going to stretch them the most. You can do this as an exercise. You already know the equation that governs all the possible initial position and initial fiber direction. You can address this question. So this is basically something that you can basically ask, which is basically equivalently you are asking IE that maximize the norm of zeta t. Right, that's what we are asking. Where should you put? Is this clear, guys? So let's say if you want to go back to this is saying, okay, now I can put every initial condition, and then I want to understand. Let's say if we are here, there is going to be now a possible set of initial perturbation vectors that I can put here, and I will ask where x0, so a maximization over x0, and where a maximization over, in this case, zeta 0 is an angle, let's say phi, for every particular x0, which one should be the one that is going to maximize the length of the perturbation the final time? And you can basically ask all these type of questions. Okay. Okay, so one more thing that I want to do is how to compute basically the deformation gradient, okay? So, you know, the deformation gradient you can do two things to compute it. Either, you know, you compute a bunch of trajectories. So you compute trajectories at all these points, and then you compute df using finite differencing. So for instance, I don't know, let's say df is at a particular x0. I mean, I'm not putting the dependence on time, but you know that f depends on time. This is gonna be what? Is gonna be the derivative of f1 with respect to x0, derivative of f1 with respect to y0, derivative of f2 with respect to x0, derivative of f2 with respect to y0. Okay, so basically if you would compute this numerically, you have to say, okay, let me actually look at the x component of the trajectory, and to compute this derivative here, I'm going to pick one point here, which is f1 at x0 plus some delta minus or plus x1 at f0 minus delta divided by 2 delta x, 2 delta. Okay, that's basically finite differencing. So you have to compute the trajectory for this point, the trajectory for this point, and do the difference, and you divide by basically the delta, which is the delta x0, and you have that entry of the derivative. Then you have to do the same, derivative of f1 with respect to y0. So you have to compute basically the derivative of x of this point, so trajectory of x starting at this point, trajectory of x starting at this point, divide by 2 delta, because you can pick the same delta in x and y, and then you estimate this point. You have to do the same for also the y components. For every point you have to do this business. So this is basically a way you can do it, just doing numerical approximation of the flow map gradient. Okay, but a more elegant way to compute basically this quantity, or you know, if you really are in systems where, because this is very sensitive, right? So this is gonna generate a lot of problem, because basically there are some regions. So let's say, what delta should you pick? There are some region in space in which your dynamics is way more sensitive. You step a little bit and there is a big variation in x, right? So then you can say, okay, I'm gonna like start shrinking delta, okay? But if you start shrinking delta, what happens is that then you have to, this calculation is, so if you shrink delta, then you have to increase also the resolution of your base grid, because otherwise you're gonna just have derivatives in very sporadic points, right? But so to resolve that, you can solve another equation, which is the equation that governs the evolution of the deformation gradient, okay? So evolution of the deformation gradient. Okay, how do you compute that? Now we're going to use the Lagrangian coordinate. So what is it? So let's go to the initial value problem, right? So we know that the derivative of the flow map, this guy, is equal to the velocity field evaluated along trajectories, right? Okay, so now what do you want to do? Look, I mean, I already know here I want to have some sort of equation for the derivative of the flow map with respect to the initial condition. Okay, so you're gonna hit this guy with El Nabla with respect to the initial condition. Okay, and what can you do here? Do you know how can I, what can I do here? I can just flip the order of integration of these two. So I'm gonna just get basically d dt. This is, by the way, the Lagrangian derivative. It's very important. This is basically the total derivative. Okay, it's just the total derivative. So d dt of gradient of x0 f t0 t x0 equal, now I have to hit this with the gradient. How do we do that? Right, so basically this guy, remember, is an x. This is our Eulerian coordinate, but unfortunately you cannot pick it. It's just picked and specified by the initial condition. So I have to do chain rule, right? First I have to differentiate this guy with respect to x, okay? And then I would differentiate the argument with respect to x0. It's as simple as that. Well, the derivative of this guy with respect to x, what is it? it's now, this is now the derivative of f with respect to x of along trajectory, right, times, so this is basically, if you will, this is the derivative of f with respect to x, times now the derivative of x with respect to x0. So this is the derivative of, with respect to x0 of the flow map. Do you agree with this? All right, I just basically did the chain rule, okay? Okay, so basically this guy is basically, we are done, because now I have a differential equation, which is a matrix differential equation for the Jacobian of the flow map. So basically you can rewrite this and say, okay, you know, df dot, I'm gonna call this basically, with the dot is the material derivatives, the total derivative is equal to dxf along trajectory. See, this is very beautiful because you have to always specify where you're evaluating these guys. These are along trajectories. If you miss this, it's over. It's very different, okay? F t0 t x0 times df. Okay, so I want to block this, all these two, and this is basically, this is called the equation of variations. Okay, let's do a couple of interpretations. So first of all, numerically, why this is beautiful? Because you say, okay, by the way, this is now a differential equation for a matrix. There is nothing fancy about it. It's just a differential equation for each entry of the matrix. So it's basically 4 differential equations. Okay? What is the initial condition for this equation? Because you need an initial condition. It's an ordinary differential equation. You need an initial condition. Okay? You also need it for a PD, but there you would need also the boundary conditions. What is the initial condition for this guy?
We have a position t0 and time x0, we have velocity.
Yeah, but when basically I set t equal to t0? Good. Yeah, yeah, but well, the matrix, not this matrix, because this is specific to this example. But what is the when you evaluate this at t0, what is it? Xf is equal to x0. So the gradient of f with respect to x0 is what? The identity matrix. Trivial, right? So basically this, you have to equip it with the initial condition plus initial condition, which is basically the df of f t0 of x0 equal to identity. Okay, then we are done. So now, so basically this is a matrix. So it looks scary, but it's very simple. So basically, for any initial condition x0, this is a differential equation of this form: b dot equal to a of t times b. Okay, and with b0 equal to identity. This you solved in, high school or maybe first years of university. It's just a matrix of it's a differential equation with the time-dependent coefficients. There is not even a forcing. Okay, why this is very useful, or this is very, very cool? Because at any point, for any point, I start with a matrix that is, let's say in 2D is 1 0 0 1. That's the identity. Then this guy, what it does, it starts percurring trajectory, so it arrives here. Okay, And then here, what you have to do, you have to say, look, now I arrived after a particular delta t, given by your integrator. You say, okay, now to evolve my 4 entries, I have just to sample the velocity gradient. This is the Jacobian of the velocity field at that particular point. And the Jacobian of the velocity field, I can sample it very simply. Actually, you can also do it in spectral, coordinates, because you have it from the PD. And then that's it. So you don't, there is no need of sophisticated derivatives, etc. You have the velocity field very well defined. So you just want to interpolate, as Anupam was saying, so, okay, I want to compute the velocity field here and actually compute the gradients of the velocity field here. And you advect and you compute at this stage, you have the gradient of f at t0 plus tau at that particular initial condition, x0i. Okay? Then you continue, you do a little bit of other, increment, just using gradients of velocities. There is no need of any fancy differentiation of the flow map, sensitivity to different, regions. So numerically, it's very convenient. I don't think you don't need to go and integrate this equation unless you have kind of a challenging system. So that's my recommendation. Most of the time you can still do finite differencing, but sometimes you can't. Okay, and why this equation is very important, because I want to now highlight one thing. So let's say let me go here. So this is going to tell us that, let's say, for instance, we go here. You're saying, okay, this was at time 0, t0. Now here I arrived at time t. Okay, and this guy, to arrive at this particular configuration, is integrated all the possible contributions of the deformation gradient along trajectory. Okay, now what is so if I want to compute the derivative of zeta t, let's say if I want to compute dt of zeta t. So if I want to understand how does basically this fiber, you understand, guys, what is this? This is basically really a piece of material that is being transported and deformed by the fluid. It's a material piece, right? So you say, okay, I can compute it, the final time, solutions for zeta t, but somehow this is sort of obscuring all the possible intermediate steps, because the flow can stretch, can shrink, and then eventually after some time you're gonna just see the end result. So it would be interesting also to understand what is instead the time derivative of this zeta t. Okay, why don't we just differentiate 1? So differentiate 1, and you're gonna get zeta t dot, what we are calling with this dot, or without the bar is the same. Now this is gonna be what? Is df dot times zeta 0. And zeta 0 doesn't depend on time, is the initial condition, right? So I just take this derivative, the only thing that depends on time is this guy, right? This is not dependent on time, it's the initial condition. Well, what is this? So I just don't want to put this bar, but this is all this. These are all the same as the total derivative. Okay? So zeta t dot is equal to dx, it's basically going to be dxf along trajectories times dx0f t0 t of x0 times zeta 0. So this is beautiful because it's going to say, it's going to tell us, look, to understand the little contribution that the velocity of zeta t at a particular time, there are two contributions that are happening. One is the Lagrangian memory. This guy says, oh, let's say, for instance, I will give a very practical example. Let me actually pick another data point. Let's say I'm here. This is my zeta, my x0, and now I start along this direction. Okay. So what happens is that the only thing that is gonna affect the dynamics of zeta 0 is the velocity gradient here. So there is going to be a particular dxf at this particular x0i t0. And this is going to tell me, look, now I'm going to start for this direction. I'm gonna start feeding some sort of a shear. Let's say that the flow does like that. So this is gonna say, look, I mean, zeta t dot is gonna be in this direction at the initial time, okay? But then let's say this guy, by a little bit of time, let's say that this guy now is doing that. This guy is gonna basically, I don't know, do particular, I don't know, maybe it's too trivial, but I mean, I can do that and say, okay, now let's say at this point, I arrived here with this my zeta t, okay? Now, what happens is that you have to sample the velocity Jacobian at this new point along trajectory. But it's very important also with which orientation you arrived here, right? Because the velocity Jacobian here is going to depend. You know, if I'm a fiber in this direction, in this direction, this direction, this direction, I'm going to feel a different velocity, okay? So let's say, for instance, here I would have a velocity field that does that. This guy wouldn't feel much, right? Because let's say if this would be the ideal profile of velocity here, right? So then, because I arrived with this particular orientation, I'm lucky enough that the velocity field is going to do very little to me, okay? But if I was instead in this direction, if I would arrive here, I would have arrived here in this particular direction. So let's say now I should transform this and make it go in some other direction. So let's say if I was here, then of course I would have felt this particular different velocity. So this guy is the Lagrangian memory. I like to think of it as Lagrangian memory or Lagrangian contribution history. And this guy is instead the instantaneous contribution. I'm going to just sample the velocity Jacobian at that particular point and then says, hey, I'm sorry, but velocity Jacobian allows you to understand derivatives in all possible directions, but I arrived there in one particular direction. That depends explicitly and only on where I started and with which direction I started. Okay, so this is instead the instantaneous contribution. Okay. Okay, so basically in a nutshell, so this is, maybe you can call this 3. Do you have questions, guys? If it's unclear, you have to stop me, of course. Okay. Okay, so the bottom line is that, so let's say mini recap, mini summary. dF governs the evolution of every possible fiber. This guy is really the queen, because you say, okay, you pick one, zeta 0, and it's going to spit out exactly the velocity of that particular perturbation at some time t, the final position of that particular perturbation, but all the juice is in the deformation gradient. Okay, so governs evolution of all material fiber. And these are just, i.e. infinitesimally small initial displacement vectors with respect to x0, because they are all based on x0, and every x0 is going to have one of those. And then, so this is 1, and equation 2 governs its evolution. And 3, so you can if you promise that you understand equation 2, you can avoid computing it from that form, but you can use finite differencing. But I really suggest you really penetrate that equation. It's beautiful. Okay, so you can avoid solving equation 2 and use finite differencing. Okay, so now the issue is the following. So this zeta is a vector, and this guy is a matrix. Okay, So basically, this is basically a tensor field. For every particular initial condition, you're going to build a matrix. In this case, it's a 2x2 matrix that is going to change its entries as you evolve the integration time. Okay, or if you would change also the initial time. Okay, so these are hard to visualize. Okay, so let me see. I'm going to. So you wrote this. I'm just going to erase this part. Okay. This. This I want. Okay, so now note observation. I would say I put it here so they have more space. Zeta t, or is a vector, and df is a matrix, so it's a tensor field. These are hard to visualize. So what you can do when because this df has a lot of information, right? That's why it's a matrix for every point that changes its coefficients as long as you change t0 or t. So, an interesting way you can start looking at, scalar quantities of this df is this one, okay? So, you can ask, what is the norm of zeta t? Okay, what is the norm of zeta t? That's a scalar. This is a vector. It's going to have basically a particular orientation and a norm. So what is the norm of zeta t? So the norm of zeta t is going to be equal just the dot product square root. So this is zeta t, okay? And this is equal to basically zeta 0. This would be df zeta 0, but I'm going to just do df transpose zeta 0. That's the norm. Okay, so basically now this is a dot product, what I indicate with these brackets, and this is a tensor, okay, and this spits a scalar, okay. So this C T0 T of x0, which is defined there, so it's basically the Jacobian of the flow map F T0 T x0 transpose times dx0 f t0 t of x0. This is called Cauchy-Green. Strain tensor. Okay, so basically, it's saying, okay, there is df there. Now I constructed, a kind of a very similar tensor, which I constructed in this particular way. And this is now the Cauchy-Green tensor, and this is the tensor that is relevant if you want to understand the norm of dt. Okay. Now we're gonna see how. So this, of course, you pick a zeta 0 is gonna spit up a scalar from this operation. So pick a zeta 0 is going to tell you exactly, pick the zeta 0 direction here, it's going to tell you the length of zeta t. Okay? Now, this is interesting because this tensor has nice properties. It's symmetric. Okay? So C is symmetric. Nice properties, basically symmetric. Do we also know a little more? Is it positive definite or negative definite, semi-definite? What is it? Why?
I think it's great.
What?
No, I was just thinking.
What does it mean for a tensor to be positive definite?
So the multiplication product should be greater than 0.
Yeah.
So
You already resolved it. You know, this is a length by construction, so it should be always positive. Yes, just because we are looking at the length, this cannot return negative value. Okay, so this is positive definite. Very good. So you gave me the exact definition. You know, an implication. You know, positive definite implies that also the eigenvalues of C will always be greater than 0. Okay, so positive definite because of what you said, because it's a length, and this implies that basically eigenvalues of C are always greater than 0. What does imply symmetry? Symmetric tensor as what? Eigenvalues and eigenvectors. Real and orthogonal eigenvectors. So this implies that basically eigenvalues are real and eigenvectors, and eigenvectors are orthogonal. Okay? This is beautiful because now that means basically because this is orthogonal, this C allows me to construct a basis on every x0, so I'm going to have a very natural basis, which I'm going to call it zeta 1. Oh, maybe let me pick something else. Actually, let me pick zeta. Zeta, I'm going to call it, I don't know, alpha 1, eigenvector number 1. This is going to be eigenvector number 2. There's going to be n of them, let's say, alpha n. And these are all now orthogonal. They're orthogonal, right? So they will basically, so these eigenvectors of C, they basically form a basis to span the vicinity of x0. For every x0, you pick this. This is a very intrinsic basis. So I can represent any perturbation in the basis of these eigenvectors. Okay? Okay. Is this clear? This is just very elementary, guys. What we do, just did the dot product. This is now, you compute this matrix, you just have to compute its transpose, multiply it by itself, you're gonna get another matrix, okay? Why this comes naturally into place is because basically if you want to understand strain, let's say if you really want to understand strain, df is not the ideal quantity because df also accounts for rotations, right? So this guy factors out the effect of rotation and is just gonna retain the information about stretching to some extent, okay? Okay, so now say, okay, you know, still, I didn't really solve much so far because I'm still gonna end up with a tensor, okay, which is gonna be hard to visualize because for every x0 now I have another tensor that also evolves its entries with you know, with time. So an interesting quantity that you can ask, or another interesting quantity that you can ask is asking, you know, this is gonna be now the finite time Lyapunov exponent, and you can ask basically what is the largest possible deformation of a material fiber zeta 0 during time interval t0 t at any point, at any x0. Okay, so what would you do that? And just let's define it. So B, now this guy is not going to depend on zeta 0 anymore, because I say, okay, let me span all the possible zeta 0 in my neighborhood. Okay, at any point. So I'm going to write this B T0 T now is going to be a function only of x0. Of what? So this guy, we are going to define it as the max over all the possible zeta 0 of this norm, zeta t divided by zeta 0. Okay, so this is, I'm just even relaxing the norm of zeta 0 equal to 1. Okay, so how do you compute this? This is this function. It's a max over all the possible zeta 0 of this quantity, you know, zeta 0, Cauchy green, zeta 0 divided by the norm of zeta 0, zeta 0. Okay? Well, I mean, because you can pick zeta 0, you can decide to have it unit norm to begin with, because this is basically, you can construct always, for every point you can construct a unit vector that spans your basically infinitesimal ball, so you can sort of eliminate this from the scheme. But if you are a little bit, if you don't believe it and you want to pick a different parameterization of zeta 0, then you just divide it by this norm. So what you can do now, because basically you can write zeta 0 as a linear combination of the local eigenvectors of C, if you do this exercise, what are you going to get? What's the maximum? Eh? What? The maximum, yeah, good. So this is going to be equal to the square root, because the square root, I keep it with me, of the largest eigenvalue of the Cauchy green, okay, at that particular position, okay? Okay, so you know, now what you have to do, it's much simpler, because you don't really have to interrogate every possible zeta 0. You compute the f by the Queen equation, that was 2, or by sort of the finite differencing, and then basically you compute Cauchy green, just transposed by itself. Now you have this matrix, compute the eigenvalue, you compute them analytically or, you know, with the command in MATLAB, and the largest eigenvalue is going to be exactly this. This is now a scalar field over the initial Lagrangian configuration of your fluid, the initial condition, and you know, this scalar field is going to now reveal a lot of structures in this flow. It's going to be a scalar field, very easy to visualize, and it's going to tell you, look, where the scalar field is very high, that means that, let's say that the scalar field would be very high here, so you would have really a ridge of very high value. So this is, let's say this would be sort of a, if I look it from this perspective, this would really be a ridge, something like that. So where now this is my x0, y0, and this would be now b t0 t of x0. So this would just be my scalar field. That would say, look, I mean, in these regions where it's high, there is going to be one particular direction which you don't know yet, that is gonna, such that if I start in that particular direction, let's say this direction, I'm going to separate at you know, maximally. So I'm going to just have maximal separation, okay? With respect to all the other directions, this is going to be a maximal one. And because you are on this I value of B, that means that also if you step out, whatever direction you pick, there is not going to be such a high separation, okay? What's the direction of largest separation? The largest eigenvector of Cauchy green. So right, so basically, so this is going to be now a scalar field of x0. Of course, it's going to depend also on t0 t, and you know, you already know for free, you get it that the largest separation will be achieved along or by the fiber aligned along the largest eigenvector of C. Okay. Now the last basically little bit is that because basically this separation grows exponentially, typically. Okay, so because at least in nonlinear systems or in chaotic systems, so typically B grows exponentially. With time. Therefore, you can define the finite time Lyapunov exponent, which is this guy, sigma T0 T of x0, which is nothing else than basically the log of square root of B, okay? Or let's call it actually largest eigenvalue. And it's fine. It's basically, we already said that that's the largest eigenvalue. No, B is already the square root. So square root of largest eigenvalue of C divided by T minus T0. Okay. So basically, if you have a linear system, the linear system, let's say if you have even a linear saddle with the stretching coefficient alpha, you would have basically that the exponential, the stretching exponent would be alpha. Okay, if you would just have a trivial linear system, x dot equal to alpha x, y dot equal to minus alpha y. Okay, the point is that when you have a nonlinear system, you cannot, depending on what you start sampling, it's going to be a very different alpha, right? Depending on the orientation, etc. However, if you want to say what would be the effective exponential stretching exponent or the affecting stretching exponent that would achieve this cumulative stretching in this time interval, that's the finite time Lyapunov exponent. It's just a generalization of a stretching exponent that takes into account the fact that basically you are moving with trajectories, okay, and you're sampling different points that have different gradients of velocities, etc. And okay, so I don't know, maybe I will stop here and maybe continue a little bit tomorrow in this direction. But the beautiful thing is that now this finite time Lyapunov exponent doesn't really depend anymore on zeta, because you really maximized over zeta, and you don't really have to do this maximization numerically, because you just have to compute the largest eigenvalue of Cauchy-Green. Okay, and of course, this FTLE is used to, as a diagnostic to understand, for instance, if there is chaos in a system, and this scalar field is also important to understand if there are different spatial structures, right, in your domain, okay? Yeah, and then maybe I'll just continue tomorrow on this. Okay, so if you want to have an exercise for this afternoon, I'll ask you, what happens, and don't ask ChatGPT, because I'm gonna interrogate whoever provides the answer. What happens when the system is linear? So if this differential equation is linear, try to understand what happens to the finite time Lyapunov exponent. Okay, think about it. Okay, all right. See you later. It's until now, right? Yeah.
Then maybe you can continue tomorrow, because also this is very math heavy, so they need time to digest and then.
Yeah, no, it's okay. Yeah.
Very rigorous.
Okay.
So we'll break for lunch and then we'll be meeting again.